Well, I take that back. They're kind of smart.
All right, well, we got that on video now. It's live. So welcome to this latest edition of Weather Basics and Ask a Meteorologist. We are joined today by Selah Middle School in Selah, Washington. Why don't you guys wave to all of those beautiful folks? Excellent. Good morning, everybody. My name is Pat Highland. I work at the National Weather Center. My fancy title is the Coordinator of External Relations, which basically means I handle all the tours, outreach, digital content, merchandising, social media. If you didn't get the picture, I'm actually the Director of Fun at the National Weather Center. I get to do all the fun stuff. If you guys ever come out to Oklahoma, I know it's a long way for you guys up there in Washington, but if you ever get a chance to come by here and check out our building, it's a really cool place. We got over 500 people that can be here at any one time. And I get to be part of all that every day here in Norman, Oklahoma. Today, I'm joined by a rock star group here. With me is Jason Laney. Jason,
Hello, everybody.
Jason works at the National Weather Service El Paso office. But as you can see in the background there, that is not the forecast office. He's at home today. So presenting from his other office at home. At the El Paso office, joining us today is Hector Crespo. Hector, how are you doing today?
Hello, everybody. I'm doing fine. How are you guys doing?
Yeah.
Excellent. So yeah, well, like I said, we've got a rock star group with us today. We are going to go over some weather basics, and then at the end, we're going to leave it open to you guys so you can ask us all those questions you could possibly think of. You guys, we're going to turn you guys into meteorologists today, so we're pretty excited about that. Jason is going to lead off our presentation today and explain to us how we get weather in the first place. So Jason, take it away.
All right, happy to do so. You know, when we first started doing this, we're in Texas, obviously. That's where El Paso is located. That's where I am right now. We were actually talking to a lot of teachers, and they were trying to teach weather to their fifth graders. Now, I know you guys are sixth graders, 1 year removed from that. And so we put this together based on some of the state testing that they had. And a lot of times people had the very same question. Where does it start? How do you get started? Where does weather come from? We know what weather is, or at least we think we do. We're kind of familiar with it. So we put together a little series of slides here. So I'm going to start you off by talking about something that I know you guys have already talked about a little bit. I've seen some of your slides from your teacher, but that is exactly what generates the weather as we know it. And believe it or not, it all starts with the sun. Yeah, that big ball of gases and explosions out there far from us in outer space, sending off light and heat and energy. Well, the sun is what really causes all of our weather. Now, you probably can imagine that the sun helps us get hot. And of course, when it's cloudy and you don't get much sun energy, it obviously gets a little cooler, but it goes so much further than that. So let's first of all talk about how the sun's energy gets here. Now, the sun gives us all different types of energy, and this energy actually arrives at the earth through a form of transfer known as radiation. So you see, there's actually several laws of radiation. One of the laws of radiation says that a good absorber is a good emitter. Another one says that every object radiates. And it also tells us that the hotter a body is, the shorter the wavelength of radiation. I know I'm getting kind of fancy for you guys right now, but imagine this. The sun, it gives off all types of radiation, but the most radiation, or the greatest percentage of radiation that comes from the sun, is what we call shortwave radiation. I'm just going to call it solar radiation to keep it simple for us. And it turns out that different things absorb different wavelengths. And when we start talking about the air around us, you know, the stuff that we're breathing right now, keeping us comfortable or making us feel cold, depending on where you are. Well, that air doesn't tend to absorb the shortwave radiation from the sun very well. Now, there are some parts of the air that will absorb it. For the most part, though, it just passes right through it like light passes through, say, the windshield of your car. So as this radiation comes from the sun, remember it's shortwave solar radiation, it doesn't get absorbed very good by the air, but it does get absorbed by the earth. And remember, I told you that one of those laws of radiation tells us that a good absorber is also a good emitter. Well, that means if the earth is going to absorb this radiation, it's also going to give this radiation back. And that's what we call outgoing terrestrial radiation, or long wave radiation. You get the idea. One's a short wave, one's a long wave. Well, it turns out that our air does absorb the long wave heat radiation pretty well. And so I like to say that the sun heats the earth, but the earth really heats the air. So if our heat source is really the earth, that makes sense why when you're close to the ground, it's warmer. And when you go higher in the sky, like up in the mountains, it's obviously going to get a little colder. So that's part of how the sun influences our weather. But if you were to compare the size of the sun to the size of the earth is kind of teeny tiny compared to the size of the sun. So we can imagine that these rays of radiation or shortwave solar radiation really kind of come to the earth in parallel lines, not necessarily radiating out in different directions. But because the earth is not flat, no, it's not, it's round, despite what you may have read on Google lately. Because of this, when the sun's rays reach the earth, they don't always reach the earth with the same angle. Notice the ones in the middle hit it right on. It's like getting a good punch in a boxing match. But the ones to the north and the ones to the south, well, they kind of come in at a little bit of an angle. It's kind of like a glancing blow, if you will. So let's take a closer look at this. And basically the idea is when the sun is more direct, straight up and down at an angle of 90 degrees, it's going to be the strongest. You're going to get the most energy or the most heating. And so as the sun comes in at different angles, lower angles than 90 degrees, you don't quite get as much. And the way I like to explain this, if you take a flashlight in a dark room and you shine that flashlight straight down on a surface, well, that light is going to be concentrated. That's what you want to do, right? You want to get all of that light energy, which is a form of radiation, by the way, in one place. But if you take that flashlight and you kind of turn it to an angle so that you spread that same amount of light out over a great distance, you know what happens? You see more stuff illuminated, but it's not as bright. Well, that's why when the sun comes in at a lower angle, it's not as intense and we don't get as much heating. So basically what I'm showing you here is the first day of spring or the first day of fall. The sun is directly over the equator on both of these days. That's where we're getting most of the heating. That's where it should obviously be the hottest. And as you go north and south, it should get progressively cooler. Now, what happens if we were to take the Earth and kind of tilt it on its side just a little bit? Imagine 23.5 degrees. I say that because the Earth is tilted on its axis 23.5 degrees. Well, this would all of a sudden take that sun that was once directly over the equator and move it north of the equator by 23.5 degrees, which we call the Tropic of Cancer, by the way. And that means that the northern hemisphere, or the part of the Earth that's north of the equator, the northern half of the Earth, is getting the most radiation. See, the sun angles are higher. So that's where it would be hot. That would be, obviously, our summer here in the northern hemisphere. But if you look south of the equator, their sun angle, even at the tropics, are pretty low. So that explains why they're going to be colder. So when it's summer on one side of the equator, it's obviously winter on the other. Now, if this is the first day of summer, how about winter? Well, it turns out in winter, the Tropic of Capricorn, which is 23.5 degrees south of the equator, is getting all of the energy from the sun. Wow, how in the world did that happen? Okay, I can understand here that it would be summer now in the southern hemisphere and winter in the northern hemisphere. But what is going on with this tilt on its axis? Now, when I talk to children a little bit younger than you, always tell them, can you imagine that the Earth is kind of wobbling one side or the other? We have trouble keeping our balance. Maybe we'd fall off, but that doesn't happen. You see, the Earth's tilt on its axis, it's always the same. It never, ever changes. What does change is the position of the Earth in relation to the sun. You see, the Earth actually revolves around the sun. You've heard about that, haven't you? Well, if you keep that angle the same and move it all the way to the left-hand side, notice how the northern hemisphere is now tilted more towards the sun. So that's our summer. First day of summer, the summer solstice. Advance it 6 months. 3 months gets us to fall. 6 months will get us on into winter there. And because the tilt is the same, but the orientation of the Earth and the sun has changed, now it's the southern hemisphere that's receiving the most energy. So it's a combination of the Earth being tilted on its axis and the fact that the Earth revolves around the sun that actually gives us our changing seasons. So if you were to look at it from just point value here on the Earth, it would look like the sun is at the equator, then it advances north of the equator for the summer, goes back to the equator for fall, then goes below the equator for winter. And that is exactly what happens. but this is how it happens for us. Isn't that kind of cool? I always like to explain that way. Now, here's another thing we need to talk about, the sun heating things up. The sun doesn't heat the earth evenly all over. Yeah, you got the idea that as you go north, it gets colder. As you go south, it gets colder. But even areas that get the same amount of energy, the same angle of the light from the flashlight, if you will, they don't always heat up the same. We found that land actually heats up a lot faster than water does. And not only does it heat up faster, it gets a lot hotter than water does too. And I like to explain this by saying if you've ever been to the beach on a nice sunny summer day, you're walking across that sand, which is the land, it's burning your feet. It's hot. That's why we wear sandals and flip-flops to the beach. But the minute you put your foot in the water, that water is so refreshingly cool and wonderful. Well, they're getting the same amount of solar energy, but remember, land heats differently than water. And if you look at our globe, our map here, we got a lot of land, but we got a lot more water. So if the land is getting hotter than the water is, that actually is going to lead to a change in pressure. Obviously, when we talk about weather, we talk about temperature. That's caused by the sun. But we also talk about something called the pressure. And I'm actually going to let Hector talk more about that in a few minutes here. But the truth of the matter is, where it gets hotter, we tend to get lower pressure. And where it's cooler, we tend to get higher pressure. So here we go with the sun not only causing differences in temperature, it's also causing differences in pressure. So the sun is causing weather. And the reason that's important is because air is always on the move. Nature's always trying to achieve a balance there. So if you have high pressure in one place and low pressure in another, that means the air is going to leave the high pressure and flow to the low pressure. And moving air is called wind. So now we've talked about the sun causing temperature changes, causing pressure changes, and causing the wind. Those are three very important things about weather that actually started with the sun. So now that we've covered all of that, I need to see if you guys have been really paying attention, okay? Here's my question. And the way we're going to do this is we're going to have Mr. Pat show your happy, smiling faces up there in Washington. And we don't all have to talk. We'll leave you muted. But I want you to do, if you think the answer to this question is 1, just hold up 1 finger. If you think the answer is number 2, 2 fingers. And we'll stop at 4 fingers. I was going to put 12 or 14, but then I realized we didn't have that many fingers. So it's real easy. Only 4 choices. And here's the question. Because the Earth is tilted at 23.5 degrees, that's that tilt on the axis, that results in what? Our cycle of day and night, something called gravity, the 4 seasons, winter, spring, summer, and fall, or the lunar cycle. What do you guys think? Mr. Pat, show them. All right, I got a lot of 3s there. I don't remember what number 3 was. You better show me the question again, Mr. Pat. They seem to think the answer is number 3. All right, Mr. Pat's going to show it back to us. The tilt of the Earth on its axis and the fact that it moves around or revolves around the sun causes, ta-da, you guys are so smart. Of course, it's number 3. It's all of our seasons. You guys may have known that before today, but if you didn't, hey, I'm happy to say we learned something. Okay, Mr. Pat, if you can present your screen to everybody one more time. Let's see if we can see this next question. There it is. When it is summer in the northern hemisphere, that's north of the equator, by the way, where we live, what season is it in the southern hemisphere, south of the equator? Is it also summer? Is it the opposite? Is it winter? Is it fall? Or is it spring? So when it's summer here, what is it down in South America? You guys are saying peace. There you go. I love it. Number 2, Mr. Pat. What was number 2? I think number 2 was winter. It was the opposite. Absolutely. When it's summer in one hemisphere, it is winter in the other. And that's because the Earth is tilted on that axis. And the areas that receive the most direct radiation are obviously going to be the hottest. Now, you guys, I've seen your slides. Those are some fantastic slides you put together. And you've taken a little deeper than I did. But due to time constraints, I'm going to leave it at that. We'll let you think about some questions, maybe a little more complicated for us coming up. We'll hopefully answer those in a little bit. But for now, I want to pass it over to my colleague in crime there at the National Weather Service in El Paso. He's really in the office. This is Mr. Hector Crespo. Hector, take it away.
Okay, thank you, Jason. So now it's time for me to talk to you about what actually the high pressure and the low pressure does to our weather. So as Jason was saying before, so here we have during a high pressure day, the first thing that happens is that we have cold air sinking down and as the air diverges up towards the ground. And then during a low pressure day, what we have is that warm air just converges and goes up into and creates clouds. As soon during high pressure, so what we usually have is clear skies, calm conditions. We would usually have dry weather, and during the day you end up getting high day temperatures, and during the night temperatures drop very low, and that's because of the air that's sinking. Then we have during a low pressure day, so that's the day of when we have bad weather. So we have cloudy skies, rain, we can even have snow, and usually after the low pressure passes through the area, then you get very cold weather. And that's because you're usually going to get what we call a cold front or a warm front. Here, that's what we're going to be looking at in the map. You have high pressure, and then you have cold air. There you have the blue triangles that are what cold front looks like. And then you have the red circles that indicate the warm front. But as you can see behind each of those lines, that's where you have your warm air behind the warm front, and your cold air is behind the cold front. Moving on, so when a cold front is passing through, so you're going to have in front of the cold front, you get warm air that starts going up as the cold front pushes the air up, and that's going to create your rain and thunderstorms. And as you can see behind the cold front, you see all the cold air that's moving the warm air up. And then during the warm front, so the process is very similar. It's just you have warm air displacing the cold air. So in that case, you don't get as many clouds, but you still get cloudiness, but not a lot of rain or thunderstorms. So, and this is how it actually looks when you're looking at it in a weather map. So before the cold front comes, you see that the temperatures in Texas, they are all around the 70s and the lower 80s. But the moment the cold front passes through, your temperatures drop like 15, 20 degrees. It can be more, it can be less. And as the front keeps moving around, so all the temperatures in the whole state just go lower. And then in the case of weather, so you have where the cold front is, where you're going to have all the thunderstorm right in front of the cold front. But right behind it, then you only get all the rain and not a lot of storms because the air is not moving up anymore. And as the cold front moves around behind the front, you can start getting less clouds as the front moves farther away from the front. And as it keeps moving towards the east, then you just keep changing the weather in that area. So with that, now we go for the questions. So here we have that the most common type of weather associated with a high pressure is either 1, cloudy skies, 2, gusty winds.
What do you think it is?
Sunny skies, or 4, thunderstorms. So what answers do we get here? So I'm seeing a lot of 2s, 3s, 2s, 3s. Okay, pretty much everybody's saying 3. So let's see. That's the correct answer. So it's sunny skies during high pressure. So now let's go to the next question. And let's see. The most vigorous weather, for example, thunderstorms, occurs with what kind of front? With a warm front, with a cold front, without a cold front, or none of the above? So let's see, what are we getting today? 2. Okay, yeah, that sounds very good. That's the correct answer. It's number 2, which is a cold front. And with that, I believe I'm passing the presentation to Pat.
Nice job, guys. So now you know how we get weather in the first place. That's because we've got the sun. You also know now why we have the wind, because the air is moving from one place to another because there's pressure differences, and you know the difference between cold fronts and warm fronts. So we're getting pretty much all the basics now. We're going to talk about probably one of the most important things on our Earth, one of the things that covers about 70% of our Earth, and that is water. Water is a pretty amazing molecule. It is the only substance that can actually exist in 3 different states. So it can exist as a solid, you guys know that as ice. It can also exist as liquid, that's water. And then it can also exist as a gas, and that's water vapor. So it's the only molecule that can do all of that. And it goes between different phases depending on certain conditions. And so you all probably heard of the water cycle before. And so this kind of shows you how water can transition from all of those different phases and where it goes. So here at the surface, like I said, 70%, more than 70% of our Earth is covered by water. So groundwater, oceans, lakes, streams, rivers, there's a lot of water there. And as the sun heats up the Earth, and then the Earth, as Mr. Jason was talking about earlier, if it heats up the Earth, you can actually get some of that water to evaporate. So evaporation is where we're changing from liquid to gas, so to that water vapor. Also, there's another way that we can actually get some form of evaporation. That's called transpiration. So there's water that's trapped inside the leaves of different plants and trees, and it can move throughout all the different veins that make up those plants and trees and various things. And it can evaporate too once it makes it out to the leaf surface. That's what we call transpiration. So as that water vapor, as it rises, it starts to cool and condense. And then, and only then, we can get some clouds to form, and that's condensation. So condensation is we've gone from a gas, so water vapor, to liquid, which is water. If enough moisture builds up inside those clouds, they begin to grow, more vertically. A lot of times we can get precipitation from that. So that's the moisture, rain, different forms. It could be even snow and ice pellets, hail, all of that falls out of the cloud and back down to the Earth. And so we get runoff from snowfall in the mountains. We also get the regular precipitation that falls into the groundwater, into oceans, lakes, streams, things like that. And that is how this water cycle all works. So you can see the different phases that are in here. So when we go from a gas to a liquid, that's condensation. And when we go from a liquid to a gas, that's evaporation. And we see when we go sometimes from a liquid to a solid, you can get snow and ice. There's other forms too. You can go, there's deposition, there's sublimation, all different sorts of ways that you can go from one of these phases of water to the next one. So this is the water cycle that we are accustomed to here on Earth. Another thing that we're accustomed to here on Earth is probably the greatest storm on Earth, and that's hurricanes. We had a pretty active hurricane season just this last year. A lot of big name hurricanes that made landfall here in the U.S. and also the U.S. territories of Puerto Rico. So how do we figure out exactly what to name all of these? So you know that hurricanes are hurricanes, tropical systems. They're all the same throughout the world, but they just have different names depending on where you are on Earth. So if you live in the central and eastern Pacific, or if you've got a tropical cyclone that's in that area, it's actually called a hurricane, just like it is here in the Atlantic. So this is where we call them hurricanes. If you have a tropical system that forms in the western Pacific, if you're on the other side of the international date line, those are called typhoons. So you may have heard Typhoon Tip was actually the largest typhoon on record, the strongest one. So those are in the western Pacific. If you're in the Indian Ocean near India and Saudi Arabia and Africa, those are called cyclones. And did you see what it says down here? Crikey, they got Willy Willies down there in Australia. So they call them Willy Willies down there. So I really wish we called ours Willy Willies. I think people would be, they'd actually pay a little bit more attention than maybe just hurricanes around here. So, so you can see tropical systems in the water. They're exactly the same all across the Earth. They're just called different things depending on where you are and where they form. So how do hurricanes form in the first place? Well, you notice a lot of times hurricanes start off as a complex of thunderstorms that start interacting with each other. You'll see them form kind of off the coast of Africa, but also in the Caribbean and in the Gulf of Mexico, and also off into the Pacific. The reason that they're able to get their act together is because the fuel source for those hurricanes is really warm ocean waters. We're talking temperatures greater than 80 degrees Fahrenheit. So you've got some really warm ocean waters out there, really close to the equators where most of these things are forming. So you got really warm ocean water because you've got those direct sun rays coming right down there onto the equator. So we talked about how we get high and low pressure because, again, we've got differences in heating across the Earth. And so you saw the picture Hector was presenting this. We have an area of low pressure. You got to make up that equilibrium. We got to get back to equilibrium. So you're going to have air flowing from high pressure to low pressure. So you can see those arrows converging in here on the low pressure area. And as that ocean water, it evaporates, it starts to rise, it cools and condenses, and it forms really tall, really big clouds. Now, one thing is, a lot of people are like, well, how do hurricanes move? The hurricanes, the storm motion for hurricanes is really the winds that are aloft. And hurricanes like to have light winds aloft, unlike tornadoes, which want to have really strong winds and differences in wind speeds and wind directions with height to get things spinning. If you have too much, that's called shear. If you have too much shear, it rips those hurricanes apart. So hurricanes like to have light winds aloft to gently steer those. And so this is how hurricanes form. So if we cut open one of these hurricanes, we can see all the different parts that make up a hurricane, and we'll talk about each one of these individual components. So the very center part of the hurricane is called the eye. You guys have probably seen pictures of that before. Surrounding the eye is, we call this the eye wall area. And then you can have spiraling rain bands really far outside of the actual hurricane center. Hurricanes can sometimes be 150 to 200 miles in diameter. So these things can be huge. And these spiraling rain bands are really far out ahead of that hurricane. So inside the eye, you have typical conditions are light winds, mostly sunny, and very low surface pressure. Wait a minute. I thought this was the greatest storm on Earth. How is the center part of this massive thing so light? Why is it so calm there? We're going to talk about why it's so calm inside that eye in just a little bit. Right outside the eye, that eye wall, the strongest thunderstorms in a hurricane are right in that area there. So we have pilots that go out with our C-130 Hurricane Hunter aircraft that's in Biloxi, Mississippi. And if there's a tropical system near the U.S. coast, they will fly directly to the eye of these tropical systems to get a central pressure measurement. Then they'll use the Saffir-Simpson scale to figure out the category of it. You got to be a pretty brave pilot because you got to drive through. You got to get through that eye wall where we've got some really big thunderstorms. The tops of those thunderstorms are going way higher than the plane can actually go. So it gets a little rough and turbulent in there. So that's where the strongest storms are. And then out here in the spiraling rain bands, you can have a lot of actually, hazardous weather. There's good chance of getting moderate and heavy rain and strong winds. And when it makes landfall, when it starts to interact with the surface there and churn and slow down a little bit, you can actually get some weak tornadoes that can form here in the rain band areas. And if it's happening over water, you could get a water spout that actually forms too over the ocean surface. So we talked about how the eye of the hurricane has light winds and low pressure. Why? Why does it do that? It should be, this is the greatest storm on Earth. It should be super turbulent inside there. Well, the reason the eye is so calm is because we saw in that previous picture showing how these hurricanes form is you've got the surface winds that are converging right in the center. You see this word on here, this term, Coriolis force. Coriolis force is a planetary force, and it's the reason why storms move certain directions depending on the size of them. So it's a planetary force that here in the northern hemisphere, it causes storms to move toward the right, and in the southern hemisphere causes them to turn to the left because of the curvature of the Earth. And so that's why you see hurricanes starting off in the right off the coast of Africa or in the Caribbean and the Gulf, and they start heading toward the US, and then they take an immediate right turn. They might make landfall, they might not. The reason they're making that right turn is because they're being influenced by the curvature of the Earth, which is Coriolis force. Now, whether certain systems have to be large enough in order for the Coriolis force to actually take effect. So tornadoes are really not impacted by the Coriolis force because they're too small. They're too small scale. But once you get up into things like hurricanes and really big high and low pressure systems, the jet stream, they are definitely impacted by this planetary force called the Coriolis force. So you've got the air converging there at the surface, but from the top, you actually have air sinking too. And you saw, when we have sinking air, we usually get happy weather. So that results in lighter surface winds. So you get a lot of sinking air there right near the top. And so that's why we have some really calm conditions inside the eye of the hurricane. So a quick quiz question for you guys here. What is the fuel source for a hurricane? Is it 1, warm ocean water? 2, peanut butter and jelly sandwiches? It's around lunchtime here. I'm getting pretty hungry. Is it 3, rotation of the earth, or 4, cold ocean water? So what do you guys think?
Which one?
What do you guys think?
Yeah.
Yeah, I'm seeing lots of 1s. I'm really sad that I'm not seeing any 2s up there. I was really hoping it was going to be peanut butter and jelly sandwiches, but no, you're correct. It's warm ocean water, so that is the fuel source. And that's why when these hurricanes make landfall, you see they go and dissipate pretty quickly because they don't have that fuel source anymore. So our last topic that we're going to talk about here before we open it up to questions for all of you guys, because we know you guys have lots of burning weather questions. And you get to talk to 3 meteorologists today. You hear the words weather and climate tossed around all over the place, but do you really know what weather and climate actually mean? So this will help you out. We're going to give you some really fun tips to remember the difference between these two. So weather is what we see in the atmosphere right now. So it's basically the current conditions in the atmosphere over a very short period of time. So this could be minutes to days. And so we express weather in terms of things like temperature, humidity, precipitation, cloudiness, visibility, and wind. So weather is on the short term. So what's happening right now? Whereas climate is happening over a long period of time. Climate's the average weather that takes place. This could be several hours, several years, hundreds, thousands, millions of years. These are things that are happening over a longer scale. So remember, weather is what's happening right now over a short period of time. And climate, we average the weather over a very long period of time to give us a general idea of what's happening across the globe instead of just looking at what is the temperature right now. So weather happens at a particular place at a particular time. So for example, the weather is the temperature right now in Selah, Washington, or what's happening down in El Paso, Texas right now, or the chance for some colder weather coming in this weekend for me here in Norman, Oklahoma, a cold front coming through. Climate is regional and long-term because we're averaging that weather over a very long period of time. So if it's news, and you all like to watch the news, it's weather. But if you are talking about history, my dear Watson, it is climate. So weather's in the news right now. Climate, that's our history. So an easy way to remember the difference between weather and climate is what you expect, and weather is what you get. So weather is what's happening right now. Climate could be like, well, what do we typically see for winters here in Oklahoma? Or what does your summer look like in Selah, Washington? So that's climate is what you expect, and weather is what you get right now. You're stuck with it. You can't get rid of it. It's weather. It's happening right now, and it's not going anywhere anytime soon. So last question here before we open it up to you guys. Hey, 50-50 chance to get it right. True or false? Climate is the average weather in a region over many years. Is that true or is that false? 1 or 2? Okay, excellent. It is in fact true. We're averaging it over a long period of time. And so you are exactly correct. Climate is the average weather in a region over many years. Climate is what you expect, and weather is what you get. Awesome job, guys. So that is the end of our Weather Basics presentation. We are going to open the floor to you guys now. We've got about 20 minutes or so to answer all of your burning weather questions. And I know you guys have a lot of them because I've seen your Google Slides and you guys have been working on putting together a lot of different types of weather information. So if you guys have any questions at all, we are here to answer those for you.
Okay, we got a couple for you. I'll go.
Why does the Earth heat faster than water?
Why does the Earth heat faster than the water? Well, let's go back to Mr. Jason because he was the one who explained all of that earlier.
All right. Well, first of all, probably the most important reason is because water is somewhat transparent and land is more opaque. And let me kind of explain that to you. So imagine if a good absorber is a good emitter, basically anything that can absorb energy is going to heat up because that's the way we transfer heat energy, okay? So let's take my arm, for instance. It's not transparent. So all of the solar energy that reaches the surface of my arm is going to get absorbed at the surface of my arm. So if 100% hits here, I absorb 100%. I get really hot. However, the water, it's transparent. And just as you can see here, you can kind of see me through the water a little bit there. So the same thing happens with the water. When the sun's energy comes in and hits the water, it doesn't get all absorbed at the top of the water. Instead, some of it gets absorbed here. Some of it penetrates a little bit deeper and gets absorbed there. Some of it goes a little bit deeper. So what you're doing with water is you're distributing the same amount of energy over a larger area. So while all of it gets a little bit of energy, none of it gets all of it, whereas the surface, because the surface isn't transparent, it all gets absorbed there. And the other thing is because water is mobile or mobile. It can move. Keep in mind, the land, unless we're having an earthquake, the land doesn't tend to move much. It just kind of sits right there. But water, whenever water starts to heat up, just like water that you put on the stove, it starts to move and roll around. We call this another form of heat transfer. If we're getting it in by radiation, well, by moving that substance, that's called convection. How about that? So not only that, because the water moves its energy from one place to the other and it absorbs it throughout its depth, water just doesn't get as hot as the land that takes it all in at one spot. Hope that makes sense.
We're talking about convection and peanut butter and jelly sandwiches. I'm getting really hungry right now. Awesome question. So that's the reason why they heat up differently. And that's why, as you saw on that large map that we had there in the US, you get areas with high and low pressure because that uneven heating and uneven pressure everywhere here on Earth. So who's got our next question?
Okay, somebody else? Bracken, you got, oh, yeah, go ahead.
Well,
You gotta speak up.
Since you live in Oklahoma, do most people that go to college just study for meteorology?
Oh, that's a really good question. So, yeah, did you guys know that, Tornado Alley here, about 80% of the world's tornadoes occur in the area that I'm currently sitting in right now. So don't worry, no chance of any severe weather today, but it's really interesting. We have one of the best meteorology programs in the country here in the National Weather Center. It's the University of Oklahoma School of Meteorology. I actually got my bachelor's and master's degrees from the University of Oklahoma here. So I got to take classes inside the National Weather Center and get degrees here. 80% of our School of Meteorology students are not from Oklahoma, which seems kind of weird. But weather, there are a lot of people all over the place that are they're interested about weather. And so they come in from other states and excuse me. I'm losing my voice. Okay. So we have a lot of people that come in from different places across the country and across the world too, because they know how great this place is to study the weather. So I think people get tired of weather and they don't want to study it anymore here in Oklahoma. So, but it's really cool. I mean, this is like, if you want to be a meteorologist, this is one of the best places in the country to do all of that stuff. So I came from Cleveland, Ohio. I had no idea Oklahoma existed on the map until I visited here in high school. So, and I saw what great program they have here. So,
Mr. Hector, where did you go to school? Did you go to school in Oklahoma?
No, I didn't went to school in Oklahoma. I went to study in Puerto Rico.
How about that? Yes, Hector is an expert in marine weather and the oceans and things of that nature. So that's why we put him to work here in El Paso in the middle of the desert. We needed somebody to help us out with all the oceans that we have around here. I went to school down in Louisiana, by the way, but if I'd had to do it all over again, I think I'd have went to OU too, Mr. Pat. I've been there to visit. It's a great school.
It's pretty awesome. And you know what? There are great meteorology programs all over the country. You guys have actually one of the best meteorology programs not too far from you. University of Washington has an awesome meteorology program. So if you guys, and I know you guys are thinking about it right now, I'm looking into every single one of your eyes and you're like, man, I want to be a meteorologist right now. Yeah, I'm seeing all of you there. You're all going to be meteorologists. Hey, you can go to University of Washington in Seattle. You can come here to Oklahoma. We're not just all, you know, we're not all riding horses and wearing cowboy hats around here. There's actually normal people that live here. So, yeah, so it's awesome. I really do encourage you, if you guys have any interest in weather, meteorology is a great field to get into.
Another question. I see some hands up there.
Who's got some questions?
I noticed you.
So pressure causes weather, but what causes the different pressure?
Oh, that goes back to the heating of the earth, right, Mr. Jason?
Yeah, it does. Keep in mind, because air is basically a fluid, just like water. I talked about how water, if you put water on the stove in a pot, you heat it from the bottom, it starts getting hot, and then it begins to move. It goes into this rolling boil. What happens? The warm water molecules move up to take the place of the colder one. Well, the air does the same thing. We just can't see it because it's invisible to us. So what happens when you have air? Basically, I like to say that pressure is the weight of the air above us. But really, if you take any little block of air, maybe what's inside my hand right here, you count the number of air molecules. If I have 1,000,000 air molecules in there, it's going to have the weight of 1,000,000 air molecules. If I only have 100,000 air molecules, it will have the weight of 100,000. So what happens? Imagine that everything is the same, okay? Nothing has really changed. It isn't really that way, but we'll just imagine that. Now here comes the sun and it's heating the earth. Remember, the earth isn't transparent, so the earth absorbs all that heat energy. And I told you that one of the laws of radiation is that a good absorber is a good emitter. So the earth gives that heat energy back to the air that's right there in contact with it, okay? So that air starts to get hot. Well, what happens when air starts to get hot? It begins to rise. So literally, we take a whole bunch of these air molecules and we move them away. So when you start taking air molecules away, the pressure down here at the surface goes down. The opposite happens when it gets cold. I love weather because weather's all about opposites. When it gets cold, cold air is very heavy and very dense, so the air molecules sink down to the ground. So if we have a certain number of air molecules and then we sink down and add a whole bunch more to it, the pressure begins to rise. So that's exactly how it's, because the air molecules are constantly in motion, warm air rising, cold air sinking. It causes different concentrations of air molecules in different spots. If you have more, you have high pressure. If you have them rise and move away, you get low pressure.
Did you guys know that you guys are perfect emitters and perfect absorbers also? Yeah, you guys are black bodies just like the sun is. So you guys experience the same stuff that the Earth does. Just obviously you're not, you know, millions of miles, you know, thousands of kilometers in diameter. Yeah, so
I am.
Oh, yeah, I was gonna say if Jason moves a little closer to the screen, he might be. So 14.92 pounds per square inch. That is essentially the weight of the air any 1 square inch area. So it's a lot. That's why, you know, you got to think the air going up to hold up those clouds, enough to hold it down, the force of gravity, it's pretty crazy. All the dynamics in the atmosphere that you just never think about. So, all right, who's got our next question?
So have you ever gone to an airplane or the weather airplane and flown into a hurricane?
I have never been on the Hurricane Hunter aircraft. I really, really want to go someday. One of the professors here in the School of Meteorology actually got to go on one of those Hurricane Hunter flights because they usually have a meteorologist on board to tell the pilots exactly where to go. Like, go into this area because it's not as scary as this area. So it's still scary. There's a lot of turbulence in there. Jason, have you ever been, actually, while you answer that, I'm going to find you guys, I'm going to show you guys pictures. I actually did get to go in a plane for weather related purposes, but I'll show you a different way.
You know, you believe it or not, I have never had the opportunity either. I've been tornado chasing. I've been real close to some tornadoes, but I've never flown into a hurricane. But my buddy over there on the corner of the screen, Mr. Hector, I have a little story to tell about him. Do you remember that last big hurricane that was in the news? I believe it was Hurricane Maria. She went right over the island of Puerto Rico. Well, like Mr. Hector said, he went to college in Puerto Rico. Actually, he grew up there. He's from the island. And because we knew that storm was coming, we sent him there to help out and work. So even though you may not have been inside the actual airplane, Mr. Hector, tell them what it's like to be inside a real hurricane on the ground.
Yeah, well, I haven't been on a hurricane hunter before. I do have friends that have gone into the airplane that goes and sees what's going on inside the hurricane. But I did experience how the Category 4 hurricane affects an island. So it's pretty much very dangerous. So you have a lot of strong winds. The wind doesn't stop howling the whole time. It lasts like hours. And then you have a lot of rain, which is something that sometimes people forget about. So you can get up to 30 to 40 inches of rain on a day with all the rain that has a hurricane. And also, besides that, then you can also have landslides due to all the rain that falls on the ground, especially on the mountains. So it's a very dangerous situation, and it ends being very catastrophic. So it's a very terrifying experience if you think about it. And it's the best way to
fun and terrifying.
No doubt.
I want to show you guys some cool photos here. Back when I was a graduate student here at OU, we had a really big field program called the Deep Convective Clouds and Chemistry Experiment, or DC3. So we were trying to study thunderstorms in Oklahoma and Texas, also up in Colorado and in Alabama. And we were flying airplanes in different parts of the storms to figure out what was happening inside those thunderstorms and certain chemicals that might be released too. I don't know if you guys know this or not, but lightning strikes actually create the most nitrous oxide of any other thing on the planet. So I got to sit inside a DC-8 aircraft in front of some really cool machines, and those are the cool machines. This was NCAR, the National Center for Atmospheric Research has a Gulfstream 5 aircraft. So before we went to go do our research, we did an intercomparison flight. So look at this. This plane, I'm not zoomed in on these pictures whatsoever. That airplane is this close to where we are in our aircraft. So there are scientists that are on that plane, and there's instruments that are on that plane collecting weather measurements in different parts of the atmosphere. And we've got a whole bunch of instruments on ours too. And so we did this intercomparison flight, and then we said bye-bye, and we went to go study some feedlots in Northeast Colorado. So we wanted to see how much methane was coming off of oil fields and feedlots. Yeah. So we had to fly above some stinky cows. I'm not zoomed in on this picture either. Those are wind turbines. We were probably 1,000 feet off the ground. So think about a big commercial airliner being about 1,000 feet off the ground. So you could see our shadow there in the field. And, we said, you know what? There's a really cool thunderstorm that's happening pretty close to the New Mexico-Texas border. So we decided to fly through the anvil of the thunderstorm. We're like, oh, hey, look at that thunderstorm over there. Let's go get it. And so you could see where all of the airplanes were set up on there, so we could figure out where we need to position ourselves to get all those measurements. So this is me just chilling out right in an anvil. Do you guys see those bubbly clouds up there? Those are called mammatus clouds. So I'm sitting right at the top of this thunderstorm, those mammatus clouds right above there. You can see the shelf cloud here with this thunderstorm. So it's pretty cool stuff. So I may not have been able to go inside a hurricane, but I've been able to do some pretty cool stuff like this too. And hey, guess what? It's at OU. So if you guys want to come to OU, but we had a lot of partners in that too. We had people from Texas Tech. We had people from Colorado State University, from lots of different universities helping us out. So look at all the cool stuff we get to do. You guys want to be meteorologists now, right? Okay, who's got our next question?
Okay, go ahead.
What's the worst storm that you've had in Oklahoma?
The worst storm that we've had in Oklahoma. We have had quite a few bad storms around here. The fastest tornado that we've ever recorded was a EF5 tornado that went through Moore, Oklahoma. So it's a town that's about 15 minutes north of us here of Norman. It was 313 miles per hour. So really big tornado, went through Bridge Creek and Moore and Oklahoma City. It almost hit the big Air Force base that we have here in Oklahoma. It's called Tinker Air Force Base. That was a really, really big tornado. There was that was part of a larger tornado outbreak that actually happened on that day. There were, I think there were almost 50 tornadoes in Oklahoma just in that one day, and over 100 in the Southern Plains. So it was a really bad outbreak of severe weather. And they had to do, there was about $1 billion worth of damage from that particular storm. So let's see what we got here. Oh, Jason's going to show us his their storm there in El Paso. So that was, for Oklahoma, that was the fastest tornado that we've ever had on record. The widest tornado that we had on record was back on May 31st of 2013, and that was in El Reno, Oklahoma. And in El Reno, that tornado was 2.6 miles wide. So think about going a couple exits and then another half of an exit. And that's how wide that tornado was. So luckily, that one occurred in kind of more of a rural area, so there really wasn't too much damage. But we had a lot of people in the El Reno area. And even when it made its way into Oklahoma City, it actually did some damage too. Jason, what about the worst storm that you guys have had there?
Well, we actually have had large hailstones. We've had hail the size of golf balls and actually up to the size of, I believe, tennis balls in some cases here. And there have been the known tornado or two, but where we live in Texas, we're in the middle of a desert. So we've got a lot of dirt and a lot of dust. One of our biggest storm problems we have here are these things that are called haboobs, or blowing dust. And this is one from just a couple of years ago. A lot of times when we get these thunderstorms, you know, thunderstorms are classified as severe when they produce winds of 58 miles per hour or greater. Well, when these thunderstorms produce those giant winds around here, they produce these huge walls of dirt that blow in called haboobs. And this is one that is approaching the university in El Paso here at where we live. And so, yeah, probably some of our worst storms turn out to be dust storms here in the desert. Can you believe that?
That's a crazy dust storm. I came to OU from Tucson, Arizona. So, yeah, I've seen haboobs before, but man, that's just crazy to see all that dust being kicked up there. Mm-hmm. Do you guys have, looks like we probably have time for maybe one or two more questions. Do you guys have any more questions for us?
Okay, a couple more.
When the planes are going in to observe the hurricanes, how are they designed to withstand the forces?
Well, that's a good question. I don't know if any plane is, specifically built to handle that stuff. The C-130 Hurricane Hunter, so C-130 is a military plane, so it's actually pretty big, and the inside of it is actually pretty hollow. The C-130s are the aircraft they use for the paratroopers, so everybody hooks themselves up to the racks on the sides, and then they propel down from really high up in the air into certain areas. So they decided to use that one for the purposes of looking inside hurricanes. And those planes are just like, they're pretty much similar to regular commercial aircraft. They can only, they go up about 30, 40,000 feet or so. But the tops of some of those thunderstorms in the eye wall are way taller than those planes can actually go. So they got to figure out a safe way to get in there as safe as they can. There's a lot of turbulence in that area. There are a couple of aircraft that we've used for severe weather. So back in the day, we had a T-28. It was a storm penetrating aircraft. They were trying to fly this airplane inside severe thunderstorms. And right now, today, we actually have We've got people at Post-Naval Graduate School in Monterey, California, and they are trying to retrofit an A-10 Warthog to fly into severe weather also. And the A-10s are actually bulletproof, and so they're hoping, hey, you know what? There's hail inside severe thunderstorms. If it can handle bullets, it can probably handle some hail too. So those people at the Post-Naval Graduate School in Monterey, California are actually retrofitting those A-10 Warthogs. So a lot of our aircraft that we use to look at severe weather, to look at other types of weather, end up being military aircraft because they're a little bit more robust than trying to put a Cessna through a storm like that. Wouldn't be a good idea.
Wow, Mr. Pat, I learned something today. That is so cool. Thanks for sharing.
Very cool. Yeah. It's funny to see, from being back in Arizona, I used to see A-10 Warthogs flying over Tucson all the time, and to know that they're going to be flying into severe weather, which Arizona doesn't see that much, it's pretty crazy to think about. So let's see. Do we have time for one more, or are we out of time for today?
Okay, we have time for one more.
Okay, perfect.
Okay, yeah, go ahead. Last one.
So I was wondering, when was the last time the climate changed?
The last time that the climate changed? Is that so? Yeah, I think that was the question. Okay. So we have a record. Remember, so climate is average weather over a long period of time, and we've been collecting climate data for a really long time. People might think, oh, you know, meteorology and climatology, it's a fairly new field. How can we have such a vast record of this stuff? Well, actually, the Earth is providing us a lot of that information. We have people in Antarctica right now that are studying ice cores that they've dug out. And these ice cores are the size of football fields. They're huge. And inside those ice cores, they actually are able to trap carbon dioxide bubbles. And so you can actually track those bubbles all the way back 500,000 years to figure out what the level of carbon dioxide is in the atmosphere. Carbon dioxide is one of those greenhouse gases. So if you add more greenhouse gases, that tends to increase that blanket, and our temperatures, our global temperatures, go up. There's a facility in Hawaii, it's on top of Mauna Loa, and we've been collecting this information for a long period of time, in addition to those ice cores and other things. And what we've noticed is, since 1880, that the global average temperature, now remember, this is a global average, so it doesn't mean all over the place exactly the same. So some areas are going to be warmer, some areas are colder. You can see that the global average temperature has increased by about 0.5 degree Celsius. So that's almost 2 degrees Fahrenheit. So if you think about that, you're probably like, okay, 2 degrees Fahrenheit, that doesn't seem like such a big deal. But think about that averaged over the entire planet. So there could be places where it is significantly warmer and other places where it's significantly colder. And that really plays an impact on what's happening with, you know, the jet stream, ocean water temperatures, ocean salinity. So there's a lot of impacts that just a small change in temperature can cause. And we've been tracking this for a long time. We've been watching those really closely because we want to do what we can to see if we can mitigate some of that warming and help out, so that we don't have, you know, when you get these drastic changes in temperature over a long period of time, it impacts weather on a small scale too. And so people are looking at extremes of weather caused by some of these different climate changes. So it has changed pretty rapidly, pretty recently. Do we have any, is that the end of our broadcast? Anybody have any other questions at all?
Yeah, I think we're questions out.
Okay, excellent. Well, I want to thank you guys once again for joining us today for Ask a Meteorologist and for Weather Basics. Again, I'm Pat Highland with the National Weather Center in Norman, Oklahoma. And today, again, from home base instead of Weather Service base, Jason Laney with the National Weather Service El Paso office, and then Hector at ground control there at El Paso office for the National Weather Service. You guys were absolutely awesome today. We hope you learned a whole lot, and keep making all of those really cool Google slides with all that sort of weather information. We hope we inspired you guys to become meteorologists at some point. If you guys want to become a meteorologist, it is an awesome field. And hey, you know what? Job security. Weather's not going anywhere. We got a lot of it to go around. So thank you so much for being with us today. You guys have an awesome rest of the day and finish up that school year strong. Bye, everybody.
Bye-bye.
Thank you. Thank you.